Hello everybody, and welcome back. We're going to be finishing off the 2017 Canadian Open paper now. We're on C4. If you haven't given it a shot, I would encourage you to do so. This is what the question looks like, and we can have a read through it, and then if you want to, pause the video and try it out before I head through the question and try and do my best on it. So what have we got for C4? Let n be a positive integer, and Sn is the numbers from 1 up to 2n. Okay. A perfect pairing of Sn is defined to be a partition of 2n numbers, of the 2n numbers, into n pairs, such that the sum of the two numbers in each pair is a perfect square. For example, if n is 4, we'd have 1, 2, 3, 4 all the way up to 7 and 8. Then a perfect pairing for S4 would be 1, 8, 2, 7, 3, 6, 4, 5. So each number belongs to exactly one pair, and you'll notice these pairs all add up to 9. And then they clarify it is not necessary for each pair to sum to the same perfect square. That just happens to be what happened here for 4. And I suspect that would happen for any Sn where 2n plus 1 is equal to a perfect square. Right, I could see that happening. Okay. Yeah, because it would split into 1, 2n, and then 2n minus 1. But what they're saying here is that there can be others. There can be other ways to do this. Okay. I kind of wish they had provided one, but oh well. Maybe we'll make one in A. So show that S8 has at least one perfect pairing. So we just need to find a perfect pairing for S8. B part, show that S5 does not have a perfect pairing. Interesting. And then C part, prove or disprove there exists a positive integer n for which Sn has at least 2017 different perfect pairings. So two pairings that are comprised of the same pairs written in a different order that are also considered, are written in a different order are considered the same pairing. So I couldn't reorder and write them out like this and call it a different ordering. It's all about what's paired with what. So at least 2017. Now, I don't think there's anything special about 2017. So I think the question in C part is really, can we make Sn so that you can get as many different perfect pairings as you want? And I think with a large enough n, we might be able to do that. But let's try A and B first, learn a bit more about perfect pairings, and see where we go. So S8. Well, let's list out S8. For this question, you would just need, you'd get full marks if you just exhibited the pairing. But if you want to explain your reasoning, that can help, especially if your pairing is off. Okay, so S8. Now, 16 is already a perfect square. And so we might try looking at ways to... So what could pair with 16, for example? Like, we might end up making a chart that says, oh, 1, you can get a perfect square if you pair 1 with 3, or 8, or 15. I guess that's it. So 1 has only a few options and so on. But 16 could be paired with, well, the next perfect square would be 25, and so you'd need 9. And then the next square after that is 36. So 16 has to be paired with 9. So 9, 16 is what we want. So that's sort of locked in. That's guaranteed. Now, we've taken 9 away, and this makes me think of 7. Because 7 and 9 could have made 16. And there's no right or wrong way to go about doing this. I mean, we might end up making a really big chart. I feel like a chart might be appropriate for S5. But I'm just playing around with it, trying to understand. Consider 7. It could be paired with... Well, you could add 2 to it to get 9. 9 to get 16. And then the next square after that would be 25, so we'd have to be paired with 18. Well, that can't happen. And the 9 can't happen. So you definitely have 2, 7. Now, what could 2 be paired with? Well, 2 could be paired with 2 to make 4, except that's impossible. It could be paired with 7 to make... Oh, no, 2's already used. Silly me. Let's try 14. So how about 14? So it could be paired with 2 to make 16, which is impossible. Or it could be paired with 11 to make 25. Or it could be paired with... No, 12 would make 26, not... No, I think 11, 14 is the only way to go about doing this. And so we're slowly just picking away at the numbers. So now, okay, 11 has been taken away. What paired with 11 quite nicely? Well, 5 could certainly do it. I think there's sort of a certain range of numbers here that only have 1 or 2 pairings, and we're slowly canceling them out. But let's look at 5. 5 could be paired with 4 to make 9, or 11 to make 16, or 20 to make 25. Well, that's out, so 4 and 5. That's done. And let's go to 12. So 12 would pair with 4 to make 16, but of course that can't happen. Or it could pair with 13 to make 25. And that's really all we can do. So you're going to have 12, 13. We are quickly running out of numbers. Now 13 makes me think of 3. 3 could pair with 6 to make... 3 could pair with 1. Finally, we get something that... so we got 1. You could pair with 6, or you could pair with 13. Of course, 13's out. So now we finally have a choice. 3 pairing with 1 or 6. And I think I'm going to try and finish this off with a little chart. 1, 3, 6, 8, 10. I think the 6 and the 10 would make a nice 16. So this is what's left over. Now you could pair 1 with 3 or 8 in order to make 9 or 15. So lots of options for 1. 3 could go with 1 or 6. 1 or 6. And that would make 9, and that's about it. 6 could go with 3 or 10. That would make 16, but we don't have 19 to make 25. 8 could go with 1 or... Well, 8 to make 16, but of course you can't use the same number twice. So that forces 1 and 8. And that takes 1 out of the running. So that means 3 has to go with 6. So now they're used, and so we finally have 10 and 15. But I like this chart here. I think we might use that for S5 to show that we can't get a pairing. And so I would just sort of summarize 1, 8, 2, 7, 3, 6, 4, 5. Oh! Well, that's kind of cool. We just sort of built up from the S4 pairing that we were given. I wonder if there's a way to extend that to maybe consider making bigger ones for C, maybe with powers of 2 or something. But that's kind of nifty that kind of a nice way to use small. And so the big numbers bigger than 8, which is 2 times 4, all sort of get paired up together. So 9 and 16. And these ones all make 9. I think the other ones all make 25, which is kind of nifty. 9, 16, what was it? 10 and 15, 11 and 14. And it really looks like this is the only way to do this as well. And 12, 13, 13, 14, 15, and 16. And that also looks kind of interesting. These are all 25s. So just having learned something from A here, just thinking ahead to maybe how we might do C is maybe chop it up into sections, and these ones here will, you can rearrange the numbers from 1 to 8, so you can pair them up so that they all add up to 9, and then the numbers from 9 to 16 become 25, and then maybe you could do 17 to 24 so that they all add up to a certain amount. But we might be able to chop things up and get lots of different ways. Now, having said that, I also just a moment ago said that it looks like there's only one way to do S8. So maybe if there is a perfect pairing, it's always unique, but I don't know. Maybe not. We'll see. Just trying to think ahead to C. I mean, maybe I won't even get to C. I mean, I'll get to C because it's, a video I have all the time I want. But as I'm thinking and doing a contest, I would like to do C, but I might run out of time, or I might want to go back and touch up something I did in like C3 or something like that. So I might not want to devote a whole chunk of time to C if I'm not entirely confident that I'm going to get it. How do I gauge whether or not I think I'm going to get 4C? Well, little thoughts like this of, do I think one way or another? Do I have a plan of attack to show that sort of thing? Could I even sort of justify it to myself briefly in my head? That's how we plan for C part. But let's move on to B, shall we? Yeah, B. So just a quick refresher. It was show that S5 doesn't have a perfect pairing. Okay. So S5, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and we go up to 2 times 5, which is 10. Okay, yeah, I think making a little chart, so make a table of possible pairings. It's always a good idea to briefly explain whatever table you're going to use. I think we'll do it vertical. So 1, what could 1 pair with? Well, it could pair with 3 to make 4 or 8 to make 9, and that's about it. 2, 3, 4, 5, 6, 7, 8, 9, 10. And there might be certain things like 10. You could use 6 to make 16, but there's no 15 to make 25, so you're sort of limited there. And so that might cause some chain reactions, and there might be one number that requires numbers that are already used. So for example, 6, you can use 3 to make 9 or 10 to make 16. That's about it. 2, you can't use another 2 to make 4, but you could use the 7 to make 9, and there's no 14 lying around. 3, you could use the 6, and there's no 13 to make 16, so that's fine. 4, you could use 5, there's no 12. 5, you could use 4. So a lot of these are just single choices. Now the 7, you could use a 2 to make 9, or you could use the 9 to make 16. And actually, I'm noticing things that we're sort of counting down, and then we're starting to count down again after a certain point as well. So the 9, nothing else with the 9 other than the 7. Now you can't use 8 there, but you can use 1 with this 8. So interesting things. You could also, silly me, you could also use a 1 with this 3 and a 6 here. There we go. And there would be a 2 here, but again, you can't use 2 and 2. That's not a good pairing. Okay, so there's, certain things that have to be done. Can we think of numbers that are sort of forced to be used one place or another? Well, it seems like 4 and 5, they pair up quite beautifully, so we can ignore them. But there might be things like, well, 9 has to go with 7, so 7, but yeah, that's all. It's consider 7. So let's write this up. 2 has to go with 7, but 9 has to go with 7. Which is impossible. And there we go. So a nice little helpful chart for no such pairing can be done. Short and sweet. Probably only worth 2 marks. And then the C part. Prove or disprove there exists a positive integer n for which Sn has 2017 different pairings. So as I said originally, I think this is probably true, just because I think you could make n big enough that there might be ways to rearrange. But how? How to do it? Well, what did we learn with S8? With S8, there was sort of this point, you chopped it off, the lower numbers, they could rearrange into these nice constant sums, and the upper numbers, they also could be rearranged. So could we do something like that, and then just have 2017 different places where we might put the cut in? That's the idea. But let's see here. So a great help would probably be, if we're trying to break this stuff up, it might be useful to say, well, could we even just get 2 different pairings? Because so far we haven't even seen pairings. And so what I'd like to do is at least take this idea of splitting the group into 2 chunks. Can I at least get 2 different pairings here? That's I think, would be helpful. Because, of course, if we can't even get 2 different pairings that easily, then maybe the answer isn't true. But I think if we split it up into a chunk, we can get a different pairing here. So, what could we do? Well, I would say the most obvious thing to do is split it up and take the first few. So obviously we need, if we pair things up, n plus 1. If we pair these up, we get a nice little sum of 2n plus 1. So we need that to be a square. Right? But if we also were to take the first, I guess, we need an even number, otherwise we don't get an even number of pairs. So the first, say, 2m here, or something like that. Yeah, first 2m, and then the last 2m. And again, how are we pairing these things up? Well, we just sort of pair the outsides and then keep going in. And that way the sum remains constant. So what's the sum over here? That would be 2, oops, keep that in red. That would be 2m plus 1, and over here would be 2m plus n plus 1. Okay, so I need nice squares like, I need these to all be squares, and m is going to have to be less than, I think, strictly less than, n. So this is the smaller square, this is a bigger square, and this is a bigger square still. So if we were to split this up, we might say, can we find an m so that 2m plus 1, we might call that a squared, and 2n plus 1, that's the sum if we're just pairing up the whole set with itself, that would be b squared, and then 2, I'm going to separate this, 2m plus 2n plus 1, we call that maybe c squared. So, yeah, there we go. Now, this is really sort of almost begging for a difference of squares, like right there now, because, for example, I see, well, there's 2n plus 1, and there's a 2n plus 1, so those could cancel out. We'd be left with 2m. But there's also 2m plus 1 and a 2m plus 1 there. I don't know, if we say c squared minus a squared is 2n. Now that's going to be useful because we care about n. And I suppose we could also say, just rather trivially, b squared minus 1, because that also leaves me with 2n. And this in a sense sort of removes n from the picture. And we could do the same thing with m, couldn't we? Because we care about an n, but we also want, once we've got an n, to be able to figure out such an m. And so if we can find an m that does this, then we'll have 2 pairings. And then it might even be the case that we could find lots of m's. So lots of different places to cut. And then we just split up into the first section, and then the last bit also pairs up to square. So that'd be nice. So can we get an expression with 2m? Well, a squared minus 1 is 2m. And then c squared minus b squared. So it's all sort of this rearrangement of this expression. C squared minus a squared is b squared minus 1. Which is technically 1 squared, I guess. Now this is 1 equation, 3 unknowns, so I suspect there's probably a lot of ways to make this happen. Any observations about the A, B's? Well, 2m plus 1 is odd, so a squared is odd, so a is odd. B is odd. In fact, c is odd as well, so that's kind of important. They all have the same parity. That's something definitely to keep in mind. If we did a difference, we can do 2 different difference of squares here. I'm very much drawn, and we could also, I guess, use this other bottom equation, but since they're rearrangements, it doesn't particularly matter to me. And n, incidentally, is b squared minus 1 over 2. B being odd, b squared is odd. B squared minus 1 would even be a multiple of 4 here. So we can definitely divide by 2. But if we were to, say, let b equal 2k plus 1, you just get some odd number in there, then we get c minus a, c plus a is equal to 2k plus 2, which is 4k k plus 1. Right? Yeah. So, having chosen a k, can we then find these c's and a's? Well, c minus a, that's going to be even, because it's a difference of odds. C plus a, that's also going to be even, difference of a sum of odd numbers. And one is strictly bigger than the other, because a's got to be positive, just like c should be positive. Is anything else we can observe? Well, we can figure out a. So if 4k times k plus, actually, since we need the factors to be even, if k times k plus 1 is equal to g times h. So if we could give for some factors. Then we could have c minus a times c plus a. And let's say that g is less than h. There's no way that the k times k plus 1 is a square, so we can definitely say that. So that's supposed to be equal to 4k k plus 1, which we could then split as 2g 2h, and that would guarantee that they're both even. So if c minus a is 2g, which would be less than 2h, would be c plus a. We could get c by saying 2g plus 2h over 2. So it would be g plus h. Now I need c to be odd. So one of gh is odd, the other must be even. So that's a useful observation. And then a would be 2h minus 2g over 2. which would, I guess, just be h minus g. I'm going to stylize this as h plus g. So, does it really just come down to choosing a k and then getting factors? And does this even work? We also need things like m has to be greater than 0, so a squared has to be greater than 1. So a can't be 1. And we also need m to be less than n. Otherwise, these are not really two sums. This would be empty. Just like if m were 0, this would be empty. So we would also need b squared definitely has to be greater than a squared because n is greater than m. So a can't be b. So we need a to be between, we need 1 less than a, less than b, less than c as well, I guess. Okay, so that's another condition to consider. There might be some more, but can we, what if I just said, okay, what if k is 1? Then q is going to be 2k plus 1, which would be 3. So then, or what am I saying? Q. B. The heck am I talking about? B. So B would be 2k plus 1, and then we'd get n is b squared minus 1 over 2. Too many m's and k's and n's and things like that going around here. Lots of variables, but I feel like we're getting close to something. And then k times k plus 1 would be 1 times 2, which does have an odd and an even factor, so that's good. G and H, odd and even factor, there we go. So we can definitely split them up like that. What else here? So the n is b squared minus 1 over 2. So I guess we really only have one, g equals 1, h equals 2. But then that would mean c is 3, and a is h minus g, which is 1. Which I guess sort of gave me an a and a c, but remember, a and b need to be different, so we can't have that. What if we tried 2? So we'd get 2 times 3 over here, which is 6. And 6 has a couple factors. We could do 1 times 6 or 2 times 3. Each of them giving me different GHs. So we'd have 1, 6, 2, 3. Again, odds and evens. I'm liking that. You'll notice the C's and the A's that we made were odd and even. So we could get, for 1, 6, C would be 7 and A would be 5. And what's B would be 5, and so that's not going to work. So this N would have been 4. What about 2, 3? So then C is 5 and A is 1. Alright, that didn't work. But we're starting expanding our horizons here. But how about K equals 3? Then Q is 7. And we're looking at K times K plus 1 is 3 times 4, which is 12. Which has some factors. So GH could be 1 and 12. It could be 2 and 6. Although we don't have an odd. We don't have two. We don't have an odd and an even here. We have 2 evens. Or we could have 3, 4. So we can't have that situation because then C would be 8. Or can we have that? So C would be 8. A would be 4. So 4, 7, and 8. What would that look like? So I wrote Q again. Darn it. What is this Q? Anyway, n would be b squared minus 1 over 2. Maybe I should have just gone with PQR. Anyways, b squared minus 1 over 2. N would be 48 over 2, so 24. So we'd be looking at 1, 2, 3, all the way up to 24. Pairing those up gives me 25. Oh, no, sorry, we go up to 2n, so it would be 48. 2n is 48. So those would add up to 7 squared, which is 49. And then where's my break supposed to be? Everything that adds up to 16, because 4 squared is 16. So if we split it there, 1 and 15 does add up to 16. 16 and 48, and so all the other ones inside here will add up to 64, which is c squared. But this isn't even, so we don't actually, there's going to be an 8 in here who doesn't get paired up with anything. So we're breaking things up. That's good. I'm liking that. But what if... Oh, I didn't do the other cases, did I? So we'd have C13 and A would be... 11. Well, I don't like that one bit. Now the A is too big. Right? Or we could have C is 7, A is 1. That doesn't work for me either. Okay, so I'm wary. I don't like that the A got big here. So I might have to watch that. What if K is 4? Well then, not Q, it's a B. I don't know. I have this impulse to write Q. And then we would have 4 times 5, which is 20. And then we could have pairings GH could be 120, 210, or 45. And again, I don't like these evens, but we would have A is 19, C is... Now I'm trying to write B when I had a C. C would be 21. Would C squared minus B squared, that'd be 40, yeah, 40 times 2, okay. And that'd be 81 minus 1. Alright. Or we'd have A is 8, C is 12, or A is 1, C is 9 again. Not liking that. Although I do like the 8, 12 again here. But that would be what? This would split up. To 63, 64 up to 80. So yeah, those ones would pair up to add up to 144. But again, we've got this odd number here. We can't have that. So I'm still looking for A being odd. Can I just get one example of that? What if we had 5? Then B would be 11. 5 times 6, 30. So we would have 130. That's looking way too big. We could have 215. There's an odd even one. We can have 310. Can't have 4. Can have 5, 6. So these are good. But I'm noticing if I do K plus 1 each time, K and K plus 1 always gives me A is 1, and C is the same as B, which is 2K plus 1. So I'd never have to list that one out again. Here, A would be 29, way too big. So, starting to realize we should limit these factors. Here, A is 13, again, way too big. Here now we'll finally have A is 7, and C is 13, at last we have some odd numbers. This is some good progress. So 1 up to 48 and 49 up to 120. So there we finally have a split. Here we finally have a pairing, or an SN. So our N would be 60, but here we finally have an SN that has two different pairings. You can either add pairwise out from the outside and then the next two closer, next two closer, and you'll get 121. Or you could go from 1 up to 48, pair those, and add up to 49, and then go from 49 to 120, and those pair up to 169. So we finally have some possibilities. Now, where to go from here? I feel like if we keep increasing k, we're going to get more and more factors for k times k plus 1, and maybe we can find some way for... I mean, I'm noticing A is bigger than B a lot, so we might have to try and find a way to limit that. But could we increase k enough so that k times k plus 1 has so many factors with one odd, one even, so that we can do this, we can split in lots of different places? Could we get a pairing that has at least 3? And let's see if we can construct one by analyzing the situation rather than just saying, well, let's try k equals 6, let's try k equals 7. So, now we want to avoid... so the problem has been, you know, we get these k's, and as I was noting with the 1 and the 30 there, the h minus g or whatever it is, whatever, it doesn't, I mean, we're assuming sort of the h is the bigger one, so I guess it is h minus g equals a. We were getting a lot of those were bigger than b, so how can we avoid that? Because b is always 2k plus 1, so we want h minus g to be less than, it's got to be strictly less than 2k plus 1, and we also need it greater than 1, so g has to be, g can't be k, h can't be k plus 1, but if you make g small, like really small, like 1, and then h is going to be k times k plus 1, that's going to be a huge difference. A huge difference. So we need a number of factors that are close together. Now, if we look anytime we have h times g equal to k equal to a number, the smaller one is always less than or equal to the square root, and the bigger one is always greater than or equal to the square root of the number that they both multiply to equal. Now, k times k plus 1 doesn't have a square root, so you can actually say that g is going to have to be between 1 and k. And you're also going to have h must be greater than or equal to k plus 1. So g is always within sort of k distance. G is confined. There's only so many values g can be. But if I want h minus g to be less than 2k plus 1, it would be really nice if we could somehow make h less than 2k plus 1 plus g. It'd be really nice if we could sort of force h to be... and I know g has a certain range, so if we could make h less than... Even if we could force h to be less than 2k plus 1 or something like that, that would even be acceptable. So, yeah, actually, maybe we should just shoot for that as a goal. H roughly less than 2k plus 1. So how can I force that? And I would need so many factors to be within this range. So, essentially, I think to answer the question, we need 2017 h's so that h is in this range. Now, g is at least 1, so I guess we could say less than or equal to 2k plus 1 or something like that if we wanted to, but that's a very narrow range. Now, the bigger k we make, the more opportunities you have for h to be in there, but they still have to be factors. So how can we make factors? I don't think... So we could always start with g equals k, h equals k plus 1. Now this is not something that we're going to allow because then a would be 1, but if k has some factors, we could maybe call this, I don't know, px. We could borrow a factor there and make this k, p times k plus 1. But then if p is greater than, I mean, p has to be at least 2, and then this will be bigger than or equal to 2k plus 2, and we're not so keen on that. So, but what if k plus 1 has some other factor, and so maybe we call it qy. Then we could swap. G could become qy, h could become... we take the p, give it to h, take the q, give it to g. And we could get something like this. And so instead of multiplying by at least 2 and therefore being bigger than 2k plus 1, our h would be multiplied by p over q, which, as long as p over q was less than 2, h would be less than 2k plus 2, and so h would be less than or equal to 2k plus 1, which would be good. That's what we just said would be nice. I'd also like to not really change oddness and evenness, so if I could make p and q odd primes, that would be nice. So can we do this? So, and I don't want g to somehow get bigger than h. So what would we need? We would need, wrong way, we would need g to get smaller. So we would need the qx that we get to be less than the px. So that tells me p is greater than q. Which is fine, because p can still be greater than q, but then this condition over here says... so we need p to be greater than q to be less than 2q. If we can do that, we should be fine. Now, if for any prime q, there's always a prime p in this range. Okay. So, what could we do? Well, we could do something like, let's start listing odd primes. So we could take these in pairs, and we could, you know, this could be q, this could be p, and this could be another q, and this could be another p. So I'm going to say something like, I think we can actually just jump to the end here. So write out the first, not 2017, but rather we need double. We need an extra amount of these things. So we'll write out the first 4,034 primes in pairs. Q1, P1, Q2, P2, and so on. All the way up to Q 2017, P 2017. I'm going to say let Q be Q1 all the way times Q 2017. I'm going to let P be P1 all the way through times P 2017. Now they don't have any factors in common. And notice that Q, what's the letter I haven't used? R. QR is less than PR, which is always less than 2QR, because P is the next prime, and so there's always a prime in this range. So just take the next prime after Q. That'll satisfy it. Incidentally, I think that result's called Chebyshev's theorem, that there's always a prime in between Q and 2Q. Anyway. So where was I? So we've got this. Q and P are relatively prime. Another way to say that is the GCD of P and Q is equal to 1. So what we can do is we can find what do we want to say? We can find Q is less than the P here, so we can find let's say S and T integers. So that I want to be careful here. Q times S plus P times T is equal to 1. And so which one do we want to? We want the Q's to become part. We want the P's to be part of G, so be part of K. So what I really want is this K to turn into P times something, and then I want the H to be capital Q times something else. So there has to be a difference of 1. Now the right way to write this up would be no, I think I want that Q and that S there. I need them to be positive, and I want PT to be the lesser one. So Q times minus S plus P times minus T is equal to -1. Oh, no, I've got it the right way. Yeah, G has the P's, H has the Q's. Okay. QS is P T plus 1, or is well, P negative T plus 1. If S and T are, or S and negative T are negative, just add in enough P times Q's to both sides. So that both are positive. And I want greater than or equal to 2, just in case there's a problem. So we can get Q times S. So P times T plus 1 is equal to Q times S. Let K equal P times T. Then K plus 1 is Q times S. Right? You can always add the same thing onto both sides, and if I add PQ to both sides, then I'll get S plus P, and I'll get P negative T plus Q plus 1. And I can add in as many PQs as I want, so I can always make S plus P. I can always make the thing multiplied by Q as big as I need, and so I can make both of these positive, and I can make both of them large enough. That's what we've got going on here. Okay. So with that in mind, Then for px, I don't think I've used x. Have I used x? I can't remember. Then for px and qx, we see that g equal to q sub x k over px is less than k and is greater than or equal to 1, and h, which is equal to px k plus 1 over qx, is greater than or equal to k plus 1, because multiplying by px over qx, this is greater than 1, this is greater than 1, less than 2, and so this is less than 2k plus 2. So h minus g, which is equal to a, is less than 2k plus 2 minus the 1 that g is at least, which is equal to 2k plus 1, which is equal to b. So we get an a less than a b. G is quite strictly less than k, and so this is also greater than k plus 1 minus 1. I guess we can put a less than sign there. And so a is within the desired range, and this happens 2017 times. So there's 2017 such GH. So 2017 ABC with c squared minus a squared equal to b squared minus 1 squared, b equal to 2k plus 1, and what was n? It's b squared minus 1 over 2. So this is a nice fixed number. A is equal to h minus g. C is equal to h plus g. And so we get at least 2017 perfect pairings. Okay, so to recap, to make multiple perfect pairings, we needed to get this sort of c squared minus a squared equals b squared minus 1 satisfied. We fix a k, that fixes a b, that fixes an n. So we're talking about the same Sn, it's just the number of different a's and c's, which is the number of ways to split into two separate groups, one of which you'll rearrange the outwards, and then outer pairs, then the second outermost pairs, and all add up to a squared, and then this larger group, the pairs will add up to c squared. And so, but there's 2017 choices of a and c, and we have specifically constructed a k so that you get this. You get these g's and these h's that are close enough together so that a is less than b, which was required. Okay. That's a lot of work. I think certainly I sort of rushed there at the end, and it can certainly be cleaned up a little bit. But yeah, getting those factors together is kind of tricky. But yeah, h being less than 2k plus 2, so definitely you don't have to worry about anything about g. G is always within k of the square root, and we just want h to be within 2k within k plus 1 of the square root, so it's got to be less than 2k plus 2. Yeah. Okay, so that finishes off the 2017 paper in its entirety. This is a long last question, but it's been a nice paper overall. So that's the 2017, so I guess the next open would be the 2018 COMC paper. Hopefully that'll be a good one. I'll look at that in the future. Until then, take care, and if you're looking for more open papers, you can find many on my channel. And if you're looking for more written style contests, I would encourage you to look at the CIMC, a little easier. The CSMC, about the same difficulty, just different styles of questions. Maybe the COMC is a little harder than the CSMC. So those are the Canadian Intermediate and Canadian Senior papers. But yeah, if you're looking for more open, I will see you in another video for that. Until then, take care.